Good morning everyone. My name is Radhika. I am a student of BSc Chemistry Honours second year. Today I am going to represent the chapter Alcohol Phenol Ether of class 12th Organic Chemistry. So let us start. Alcohol, phenol and ether are the basic compounds for the formation of detergents, antiseptics and fragrance respectively. You have learned that substitution of one or more hydrogen atom from a hydrocarbon by another atom or a group of atoms result in the formation of an entirely new compound having altogether different properties and application. Alcohol and phenol are formed when a hydrogen atom in a hydrocarbon, aliphatic and aromatic respectively, is replaced by a OH group. These classes of compound find wide application in industry as well as in day-to-day life. For instance, you have ever noticed that ordinary spirit used for polishing wooden furniture is chiefly a compound containing hydroxyl group ethanol. The sugar we eat, the cotton used for fabrics, the paper we use for writing are all made up of compound containing OH groups. Just think of life without paper. No notebooks, books, newspaper, currency notes, checks, certificates, etc. The magazines carrying beautiful photographs and interesting story would disappear from our life. It would have been really a different world. An alcohol contains one or more hydroxyl group directly attached to the carbon atom of an aliphatic system, while a phenol contains OH group directly attached to the carbon atom of an aromatic system. The substitution of a hydrogen atom in a hydrocarbon by an alkoxy or aryl oxy group yield another class of compound known as ether. For example, CH3O CH3 dimethyl ether. You may also visualize ether as a compound formed by substituting the hydrogen atom of hydroxyl group of an alcohol or phenol by an alkyl or aryl group. In this unit, we shall discuss the chemistry of three classes of compound, namely alcohol, phenol, and ether. The classification of compounds makes their study systematic and their hence simpler. Therefore, let us first learn how our alcohol phenol are classified. Mono, di, tri, or polyhydric compounds. Alcohol and phenol may be classified as mono, di, tri, or polyhydric compounds depending on whether they contain one, two, three, or many hydroxyl groups respectively in their structure as given below. Monohydric, dihydric, or trihydric. Monohydric alcohol may be further classified according to the hybridization of carbon atom to which the hydroxyl group is attached. Compound containing carbon sp3 OH bond. In this class of alcohol, the OH group is attached to an sp3 hybridized carbon of an atom of an alkyl group. They are further classified as follows: primary, secondary, and tertiary alcohol. In this three type of alcohol, the OH group is attached to primary, secondary, and tertiary carbon atom respectively as depicted below. Primary, secondary, and tertiary alcohol are structured given above. Allylic alcohol. In this alcohol, the OH group is attached to the sp3 hybridized carbon next to the carbon-carbon double bond, that is, to an allylic carbon. For example, here are the structure of the primary, secondary, and tertiary allylic alcohol. Benzylic alcohol. In this alcohol, the OH group is attached to the sp3 hybridized carbon atom next to an aromatic ring. For example, here the structure given of primary, secondary, and tertiary alcohol. Allylic and benzylic alcohol may be primary, secondary, or tertiary. Compound containing carbon sp2 OH bond. These alcohol contain OH group bonded to a carbon-carbon double bond, that is, to a vinylic carbon or to an aryl carbon. These alcohol are known as vinylic alcohol. Vinylic alcohol CH2 double bond CH single bond OH. Phenols. Ether are classified as a simple symmetrical if the alkyl or aryl group attached to the oxygen atom are the same and mixed or unsymmetrical. If the two groups are different, diethyl ether C2H5O C2H5 is a symmetrical ether, whereas C2H5O CH3 and C2H5O C6H5 are unsymmetrical ethers. Nomenclature. Alcohol. The common name of alcohol is derived from the common name of alkyl group and adding the word alcohol to it. For example, CH3OH is a methyl alcohol. According to the IUPAC system, Unit 12th, Class 11th, the name of an alcohol is derived from the name of alkane from which the alcohol is derived. By substituting E of alkane with the suffix "ol", the position of substituent are indicated by numerals. For this, the longest carbon chain, parent chain, is numbered starting at the end nearest to the hydroxyl group. The position of OH group and other substituents are indicated by using the number of carbon atoms to which these are attached. For naming polyhydric alcohol, the E of a alkane is retained and ending "ol" is added. The number of OH group is indicated by adding the multiplicative prefix di, tri, etc. before "ol." The position of OH group are indicated by appropriate locants. HO CH2CH2OH is named as ethane 1,2-diol. Table 11.2 given the common names and IUPAC name of few examples, such as CH3OH is a compound which common name is methyl alcohol and IUPAC name is methanol. Same as CH3CH2CH2OH and propyl alcohol propan-1-ol. CH3CHOHCH3 isopropyl alcohol propane-2-ol and so on. Cyclic alcohol are named using the prefix cyclo and considering the OH group attached to the carbon 1. Here are the structure of cyclohexanol and 2-methyl cyclopentanol. Next one is phenol. Phenol. The simplest hydroxy derivative of benzene is phenol. It is a common name and also accepted as a IUPAC name. As structure of phenol involves a benzene ring in its substituent compound. The term ortho means 1,2-di substituted, meta 1,3-di substituted, and para 1,4-di substituted are often used in a common names. Here are the structure of some compounds like phenol with their common names and IUPAC name. Phenol orthocresol 2-methyl phenol, metacresol 3-methyl phenol, paracresol 4-methyl phenol. Dihydroxy derivative of benzene are known as 1,2, 1,3 and 1,4 benzeno-diol. Common name catechol, IUPAC name benzene 1,2-diol. Resorcinol benzene 1,3-diol. Hydroquinone or quinol benzene 1,4-diol. Ether. Common name of ether are derived from a name of alkyl aryl group as separate word in alphabetical order and adding the word ether at the end. For example, CH3O C2H5 is a ethyl methyl ether. Compound CH3O CH3 dimethyl ether and methoxymethane. C2H5O C2H5 diethyl ether ethoxyethane. CH3O CH2 CH2 CH3 methyl and propyl ether 1-methoxypropane and so on. If both the alkyl group are the same, the prefix di is added before the alkyl group. For example, C2H5O C2H5 is a diethyl ether. According to the IUPAC system of nomenclature, ether is regarded as a hydrocarbon derivative in which a hydrogen atom is replaced by an OR and OAR group, where R and A are represent alkyl and aryl groups respectively. The larger R group is chosen as a parent hydrocarbon. The name of few ether are given as example 11.2. Structure of functional group. In alcohol, the oxygen of OH group is attached to the carbon by a sigma bond formed by an overlap of sp3 hybridized orbital of carbon with the sp3 hybridized orbital of oxygen. Figure 11.1 depicts structural aspect of methanol, phenol and methoxymethane. Here are some structural aspects with the bond angles between them: methanol, phenol and methoxymethane. The bond angle in alcohol is slightly less than the tetrahedral angle, that is 109-28 degree. It is due to the repulsion between the unshared electron pair of oxygen in phenol. The OH group is attached to a sp2 hybridized carbon of an aromatic ring. The carbon-oxygen bond length 136 picometer in phenol is slightly less than that in methanol. This is due to the partial double bond character on the account of conjugation of unshared electron pair of oxygen with the aromatic ring. Section 11.4.4 and second, sp2 hybridized state of carbon to which oxygen is attached. In ether, the 4 electron pair, that is 2 bond pair and 2 lone pair of electrons on oxygen are arranged approximately in a tetrahedral arrangement. The bond angle is slightly greater than the tetrahedral angle due to the repulsive interaction between the two bulky R groups. The carbon-oxygen bond length 141 picometer is almost the same as in alcohol. 11.4 Alcohol and phenol. Let us discuss about the preparation of alcohol. Alcohol are prepared by the following methods. First, from alkenes. How can we prepare? Let's see. First, by acid catalyzed hydration. Alkene reacts with the water in the presence of acid as a catalyst to form alcohol. In case of unsymmetrical alkene, the addition reaction takes place in accordance with Markovnikov rule. Unit 13, class 11th. CH2 CH double bond CH plus H2O gives CH3 CHOH CH3. Mechanism. The mechanism of a reaction involves the following 3 steps. Step 1. Protonation of alkene to form carbocation by electrophilic attack of H3O positive. H2O plus H positive gives out H3O positive. Here are the mechanism. Step 2. Nucleophilic attack of water on carbocation. Step 3. Deprotonation to form an alcohol. Second method, by hydroboration oxidation. Diborane BH3 whole twice reacts with alkene to give trialkyl borane as an addition product. This is oxidized to alcohol by hydrogen peroxide in presence of aqueous sodium hydroxide. CH3CH double bond CH2 plus HBH2 whole twice gives out CH3CHH CH2BH2. Add more propene into it, CH3CH2 CH2 whole twice BH. Excess propene, CH3CH2 CH2 thrice B. Water, CH3CH2 CH2OH plus BOH thrice, hence propanol is prepared. The addition of borane to a double bond takes place in such a manner that the boron atom gets attached to the sp2 hybridized carbon carrying greater number of hydrogen atoms. The alcohol so formed looks as if it has been formed by addition of water to the alkene in a way opposite to the Markovnikov rule. In this reaction, alcohol is obtained in an excellent yield. Second, from carbonyl compounds by the reduction of aldehyde and ketones. Aldehyde and ketones are reduced to the corresponding alcohol by addition of hydrogen in presence of catalyst. The usual catalyst is a finely divided metal such as platinum, palladium or nickel. It is also prepared by treating aldehyde and ketone with a sodium borohydride NaBH4 or lithium aluminum hydride LiAlH4. Aldehyde yield primary alcohol whereas ketone gives secondary alcohol. RCHO plus H2 gives out RCH2OH in presence of palladium catalyst. RCOR- gives out RCHOHR- in presence of NaBH4. Second, by reduction of carboxylic acid and esters. Carboxylic acids are reduced to primary alcohol in excellent yield by lithium aluminum hydride, a strong reducing agent. RCOOH gives out RCH2OH in presence of water and LiAlH4. However, LiAlH4 is an expensive reagent and therefore used for preparing special chemicals only. Commercially, acids are reduced to alcohol by converting them to the esters, followed by their reduction using hydrogen in presence of catalyst. RCOOH gives RCOOR in presence of ROH and H positive gives RCH2OH plus ROH in presence of H2 catalyst. Third, from Grignard reagent. Alcohol are prepared by the reaction of Grignard reagent unit 10th class 12th with aldehyde and ketones. The first step of reaction is the nucleophilic addition of Grignard reagent to the carbonyl group to form an adduct. Hydrolysis of the adduct yield an alcohol. Here are the mechanism of this. The overall reaction using different aldehyde and ketones are follows. HCHO plus RMgX gives out RCH2OMgX gives RCH2OH plus MgOHX in presence of water. RCHO plus R-MgX gives out RCHR-OMgX gives out RCHR-OH plus MgOHX in presence of water. RCOR plus RMgX gives RCRR-OMgX gives out RCRR-OH plus MgOHX. You will notice that the reaction produces a primary alcohol with methanol, a secondary alcohol with other aldehyde and tertiary alcohol with the ketones. 11.4.2 Preparation of phenol. Phenol, also known as a carbolic acids, was first isolated in the early 19th century from coal tar. Nowadays, phenol is commercially produced synthetically in laboratory. Phenols are prepared from benzene derivative by any of the following methods. First, from haloarenes. Chlorobenzene is fused with the NaOH at 623 Kelvin and 320 atmospheric pressure. Phenol is obtained by acidification of sodium phenoxide soap reduced. Unit 10, class 12th. Second, from benzene sulfonic acid. Benzene is sulfonated with oleum and benzene sulfonic acid, so formed is converted to sodium phenoxide on heating with molten sodium hydroxide. Acidification of sodium salts give phenol. Third, from diazonium salts. A diazonium salt is formed by treating an aromatic primary amine with nitrous acid NaNO2 plus HCl at 273 to 278 Kelvin. Diazonium salts are hydrolyzed to phenol by warming with water or by treating with dilute acids. Unit 13, class 12th. Here are the structure of aniline, benzene diazonoyl chloride, phenol plus N2 plus HCl. Fourth, from cumene. Phenol is manufactured from the hydrocarbon cumene. Cumene isopropyl benzene is oxidized in presence of air to cumene hydroperoxide. It is converted to phenol and acetone by treating it with dilute acid. Acetone, a byproduct of this reaction, is also obtained in large quantities by this method. Cumene hydroperoxide, and so on gives in the reaction. 11.4.3 Physical properties. Alcohol and phenol consist of two parts, an alkyl aryl group and a hydroxy group. The properties of alcohol and phenols are chiefly due to the hydroxyl group. The nature of the alkyl and aryl group simply modify these properties. Boiling points. The boiling point of alcohol and phenol increase with the increase in number of carbon atoms, increase in van der Waals forces. In alcohol, the boiling point decreases with the increase of branching in a carbon chain because of decrease in a van der Waals forces with a decrease in a surface area. The OH group in alcohol and phenol is involved in a intermolecular hydrogen bonding as shown below. ROH, HOR, HOR, and so on. It is interesting to note that boiling point of alcohol and phenol are higher in comparison to the other classes of compound, namely hydrocarbon, ether, haloalkenes, and haloarenes of comparable molecular masses. For example, ethanol and propane have comparable molecular masses, but their boiling point differ widely. The boiling point of methoxymethane is intermediate of two boiling points. The high boiling point of alcohol are mainly due to the presence of intermolecular hydrogen bonding in them, which is lacking in ether and hydrocarbon. Solubility. Solubility of alcohol and phenol in water is due to their ability to form hydrogen bond with the water molecule as shown. The solubility decreases with the increases in the size of aryl alkyl hydrophobic group. Several of the lower molecular mass alcohol are miscible with water in all proportions. (11.4.4) Chemical reactions. Alcohol are versatile compounds. They react both as nucleophiles and electrophiles. The bond between OH is broken when alcohol reacts as a nucleophile. Alcohol as a nucleophile. Here are the steps. Second, the bond between CO is broken when they act as an electrophile. Protonated alcohol react in this manner. Protonated alcohol as electrophile. Here are the mechanism. Based on the cleavage of OH and CO bond, the reaction of alcohol and phenol may be divided into two groups. Reaction involving cleavage of OH bond. Acidity of alcohol and phenol. First, reaction with metals. Alcohol and phenol react with the active metals such as sodium, potassium, and aluminium to yield corresponding alkoxide, phenoxide, and hydrogen. 2ROH plus 2Na gives out 2RONA sodium alkoxide plus H2. Tertiary butyl alcohol plus 2 aluminium molecules gives out aluminium tertiary butoxide. In addition to this, phenol plus Na gives out sodium phenoxide. In addition to this, phenol react with the aqueous sodium hydroxide to form a sodium phenoxide. Phenol plus NaOH gives sodium phenoxide plus H2. The above reaction shows that alcohol and phenol acidic in nature. In fact, alcohol and phenol are Bronsted acids. They can donate a proton to a strong base. Base acid gives out conjugated acid plus conjugate base. Second, acidity of alcohol. The acidic character of alcohol is due to the polar nature of OH bond. An electron releasing group, methyl, ethyl, increases electron density on oxygen, tendency to decrease the polarity of OH bond. This decreases the acid strength for this reaction. The acid strength of alcohol decreases in the following order: primary, secondary, as well as tertiary. Alcohol are, however, weaker acids than water. These can be illustrated by the reaction of water with an alkoxide. Base acid, conjugated acid plus conjugated base. This reaction shows that water is a better proton donor, strong acid, than alcohol. Also, in above reaction, we note that an alkoxide ion is a better proton acceptor than hydroxide ion, which suggests that alkoxide are stronger bases. Sodium ethoxide is a stronger base than sodium hydroxide. Alcohol acts as a Bronsted bases as well. It is due to the presence of unshared electron pair on oxygen, which makes them proton acceptor. Third, acidity of phenol. The reaction of phenol with the metals, example sodium aluminium, and sodium hydroxide indicates its acidic nature. The hydroxyl group in phenol is directly attached to the carbon, the sp2 hybridized carbon of benzene ring, which act as the electron withdrawing group. Due to this, the charge distribution in phenol molecule, as depicted in its resonance structure, causes the oxygen of OH group to be positive. Here are the resonating structure of the phenol. This reaction of phenol with aqueous sodium hydroxide indicate that phenol are stronger acid than alcohol and water. Let us examine how a compound in which a hydroxyl group attached to an aromatic ring is a more acidic than the one in which hydroxyl group is attached to an alkyl group. The ionization of an alcohol and a phenol takes place as follows. ROH gives RO negative plus H positive. Due to the higher electronegativity of sp2 hybridized carbon of phenol to which OH is attached, electron density decreases on oxygen. This increases the polarity of OH bond and results in an increase in ionization of phenol than that of alcohol. Now let us examine the stabilizers of alkoxide and phenoxide ion. In alkoxide ion, the negative in alkoxide ion, the negative charge is localized on oxygen, while in a phenoxide ion the charge is delocalized. The delocalization of negative charge makes phenoxide ion more stable and favor the ionization of phenol. Although there is also charge delocalization in phenol, its resonance structure have a charge separation due to which the phenol molecule is less stable than phenoxide ion. Here is the resonating structure of the phenoxide ion. In substituent phenol, the presence of electron withdrawing groups such as nitro group enhancing the acidic strength of phenol. This effect is more pronounced when the such group is present in ortho and para position. It is due to the effective delocalization of a negative charge in phenoxide ion. On the other hand, electron releasing groups such as alkyl group in general do not favor the formation of phenoxide ion, resulting in decrease in acid strength. Cresol, for example, are less acidic than phenol. pKa values of some phenol and ethanol. Ortho nitrophenol formula 7.2, beta-nitrophenol 8.3, para-nitrophenol 7.1, phenol 10, orthocresol 10.2, metacresol 10.1, paracresol 10.2, ethanol 15.9. From the above data, you will notice that phenol is a million times more acidic than ethanol. Esterification. Alcohol and phenol react with the carboxylic acid chloride and acid anhydride to form esters. ArRO plus H plus R dash COOH gives ArROCOR dash plus H2 and so on. The reaction with the carboxylic acid and acid anhydride is carried out in the presence of a small amount of concentrated sulfuric acid. The reaction is reversible and therefore water is removed as soon as it formed. The reaction with the acid chloride is carried out in presence of a base as to neutralize HCl, which is formed during the reaction. It shifts the equilibrium to the right hand side. The introduction of acetyl CH3CO group in alcohol or phenol is known as acetylation. Acetylation of salicylic acid produces aspirin. Salicylic acid plus CH3CO whole twice O gives acetyl salicylic acid, which is aspirin, plus CH3COH in presence of H positive. Reaction involving cleavage of carbon-oxygen bond in alcohol. The reaction involving cleavage of carbon-oxygen bond takes place only in alcohol. Phenol show this type of reaction only with zinc. Reaction with a hydrogen halide. Alcohol react with a hydrogen halide to form alkyl halide. Refer Unit 10, Class 12. ROH plus HX give RX plus H2O. The difference in the reactivity of three classes of alcohol with HCl distinguish them. The difference in the reactivity of three classes of alcohol with HCl distinguish them from one another. Lucas test. Alcohol are soluble in Lucas reagent, concentrated HCl and ZnCl2, while their halides are immiscible. and produce turbidity in solution. In case of tertiary alcohol, turbidity is produced immediately as they form the halide easily. Primary alcohol do not produce turbidity at room temperature. Reaction with the phosphorus trihalide. Alcohol are converted to alkyl bromide by reaction with phosphorus tribromide. Refer Unit 10, Class 12. Dehydration. Alcohols undergo dehydration, removal of a molecule of water to form alkenes. On treating with a protic acid, example concentrated H2SO4 or H3PO4, or catalyst such as anhydrous zinc chloride or alumina. Unit 13, Class 11th. CH3CH2O gives alkene plus H2O in presence of H positive in heat. Ethanol undergoes dehydration by heating with a concentrated H2SO4 at 443 Kelvin. C2H5OH gives ethene plus H2O in presence of H2SO4 4443 Kelvin. Secondary and tertiary alcohol are dehydrated under milder conditions. For example, CH3CHOH CH3 gives out CH3CH double bond CH2 plus H2, 85% H3PO4, 4400 Kelvin. Thus, the relative ease of dehydration of alcohol follows the following order: tertiary, secondary, and primary. The mechanism of dehydration of ethanol involves the following steps. Mechanism. Step 1. Formation of protonated alcohol. Ethanol gives out a protonated alcohol, ethyloxynium ion, which is a fast reaction. Step 2. Formation of carbocation. It is the slowest step and hence the rate determining steps of the reaction. Step 3. Formation of ethene by elimination of a proton. The acid used in step 1 is released in step 3 to drive the equilibrium to the right. Ethene is removed as it is formed. Fourth, oxidation. Oxidation of alcohol involves the formation of carbon-oxygen double bond with the cleavage of an OH bond and CH bond. Such a cleavage and a formation of bond occur in an oxidation reaction. These are also known as a dehydrogenation reaction, as these involve loss of dihydrogen from an alcohol molecule. Depending on the oxidizing agent used, as a primary alcohol is oxidized to an aldehyde, which in turn is oxidized to a carboxylic acid. RCH2OH oxidation, aldehyde gives out carboxylic acid. Strong oxidizing agents such as acidified potassium permanganate are used for getting carboxylic acid from alcohol directly. CrO3 in an anhydrous medium is used as an oxidizing agent for the isolation of aldehyde. RCH2OH gives RCHO in presence of CrO3. A better reagent for oxidation of primary alcohol to aldehyde in a good yield is pyridinium chlorochromate (PCC), a complex of chromium trioxide with a pyridine and HCl. CH3CH double bond CH, CH2OH gives out CH3CH double bond CH, CHO in presence of PCC. Secondary alcohol are oxidized to ketone by a chromic anhydride CrO3. Secondary alcohol gives out a ketone in presence of CrO3. Tertiary alcohol do not undergo oxidation reaction. Under strong reaction conditions such as oxidizing agent and elevated temperature, cleavage of a various C-C bond takes place and a mixture of carboxylic acid containing lesser number of carbon atom is formed. When the vapors of the primary or secondary alcohol are passed over heated copper at 573 Kelvin, dehydrogenation takes place and the aldehyde or the ketone is formed, while tertiary alcohol undergo dehydration. Biological oxidation of methanol and ethanol in a body produces the corresponding aldehyde followed by the acid. At times, the alcoholics by mistakes drink ethanol mixed with the methanol are also called denatured alcohol. In the body, methanol is oxidized first to methanol and then to methanoic acid, which may cause blindness and death. A methanol poisoned patient is treated by giving intravenous infusions of diluted ethanol. The enzyme responsible for oxidation of aldehyde is swept, allowing time for kidney to excrete methanol. Reaction of phenol. Following reaction are shown by phenols only. Electrophilic aromatic substitution. In phenols, the reaction that takes place on aromatic ring are electrophilic substitution reaction, unit 13, class 12th. The OH group attached to the benzene ring activate it towards electrophilic substitution. Also, it directs the incoming groups to ortho and para position in the ring as these positions become electron rich due to the resonance effect caused by hydroxyl group. The resonance structure are shown under acidity of phenols. Common electrophilic aromatic substitution reaction taking place in a phenol are as follows. Nitration. With dilute nitric acid at a low temperature, phenol yield a mixture of ortho and para-nitrophenol. Phenol gives out orthonitrophenol and para-nitrophenol in presence of dilute HNO3. The ortho and para isomer can be separated by a steam distillation. Orthonitrophenol is a steam volatile due to the intermolecular hydrogen bonding, while para-nitrophenol is less volatile due to the intermolecular hydrogen bonding which cause the association of molecule. Orthonitrophenol intermolecular hydrogen bonding, para-nitrophenol intermolecular hydrogen bonding. With concentrated acid, phenol is converted into 2,4,6-trinitrophenol. The product is commonly known as a picric acid. The yield of reaction product is poor. Phenol gives out 2,4,6-trinitrophenol picric acid in presence of concentrated HNO3. Nowadays, picric acid is prepared by treating phenol first with a concentrated sulfuric acid, which convert it to the phenol 2,4-disulfonic acid, and then with concentrated nitric acid to get 2,4,6-trinitrophenol. Can you write the equation of the reaction involved? Second, halogenation. On treating phenol with the bromine, different reaction products are formed under different experimental conditions. First, when a reaction is carried out in a solvent of low polarity such as CHCl3 or CS2 and at a low temperature, monobromophenol are formed. Phenol give out Bromophenol as a major and a minor product in presence of Br2 in CS2 at 273 Kelvin temperature. The usual halogenation of benzene takes place in the presence of Lewis acid such as FeBr3 unit 10 class 12 which polarizes the halogen molecule. In case of phenol, the polarization of bromine molecule takes place even in absence of Lewis acid. It is due to the highly activated effect of OH group attached to the benzene ring. When phenol is treated with the bromine water, 2,4,6 tribromophenol is formed as a white precipitate. Second, Colbase reaction. Phenoxide ion generated by treating phenol with the sodium hydroxide is even more reactive than phenol towards electrophilic aromatic substitution. Hence, it undergoes electrophilic substitution with carbon dioxide, a weak electrophile. Orthohydroxybenzenoic acid is formed as the main reaction product. Phenol gives out ONA, presence of NaOH, gives out hydroxybenzoic acid, which is a salicylic acid in presence of CO2 in H positive. Third, Riemel-Timel reaction. On treating phenol with chloroform in presence of sodium hydroxide, a CHO group is introduced at the ortho position of benzene ring. This reaction is known as a Riemel-Timel reaction. The intermediate substituted benzyl chloride is hydrolyzed in presence of alkali to produce salicylaldehyde. Reaction of phenol with zinc dust. Phenol is converted to the benzene on heating with zinc dust. Oxidation. Oxidation of phenol with chromic acid produces a conjugated diketone known as a benzoquinone. In the presence of air, phenol are slowly oxidized to dark colored mixture containing quinones. Some commercially important alcohols. Methanol and alcohol are among the two commercially imported alcohols. Methanol, CH3OH, also known as a wood spirit, was produced by a destructive distillation of wood. Today, most of the methanol is produced by a catalytic hydrogenation of carbon monoxide at high pressure and temperature and in presence of ZnOCr2O3 catalyst. Methanol is a colorless liquid and boils at 337 Kelvin. It is a highly poisonous in nature. Ingestion of even small quantities of methanol can cause blindness and large quantities cause even death. Methanol is used as a solvent in paints, varnishes, and chiefly for making formaldehyde. Ethanol, C2H5, is obtained commercially by fermentation. The oldest method is from sugar. The sugar is molasses, sugarcane or fruit such as grapes is converted into glucose and fructose, both of which have the same formula, C6H12O6, in presence of an enzyme invertase. Glucose and fructose undergo fermentation in presence of another enzyme, zymase, which is found in yeast. C12H22O11 plus H2O gives out glucose plus fructose in presence of invertase. Same as C6H12O6 gives out 2C2H5OH plus 2CO2 in presence of an enzyme zymase. In winemaking, grapes are the source of sugar and yeast. As grapes ripen, the quantity of sugar increases and the yeast grow on the outer skin. When grapes are crushed, sugar and the enzyme come in a contact and a fermentation starts. Fermentation takes place in an anaerobic condition. In absence of air, carbon dioxide is released during fermentation. The action of zymes is inhibited once the percentage of alcohol formed exceeds 14%. If air get into fermentation mixture, the oxygen of air oxidized ethanol to ethanoic acid, which in turn destroy the taste of Ethanol is a colorless liquid with the boiling point of 351 Kelvin. It is used as a solvent in a paint industry as in the preparation of a number of carbon compounds. The commercial alcohol is made unfit for drinking by mixing in it some copper sulfate to give it a color and a pyridine, a foul smelling liquid. It is known as denaturation of alcohol. Nowadays, large quantities of ethanol are obtained via the hydration of ethene. Preparation of ether by dehydration of alcohol. Alcohol undergo dehydration in presence of protic acids H2SO4 and H3PO4. The formation of a reaction product, alkene or ether, depends on the reaction conditions. For example, ethanol depends on the reaction condition. For example, ethanol is dehydrated to ethene in presence of sulfuric acid at 443 Kelvin. At 413 Kelvin, ethoxyethane is the main product. CH3CH2OH gives ethene and ethoxyethane in presence of H2SO4 and at 443 and 413 Kelvin temperature. The formation of ether is a nucleophilic biomolecular reaction SN2 involving the attack of alcohol molecule in a protonated alcohol as indicated below. Acidic dehydration of alcohol to give an alkene is also associated with a substitution reaction to give an ether. The method is suitable for the preparation of ether having primary alkyl groups only. The alkyl group should be unhindered at the temperature be kept low. Otherwise, the reaction favors the formation of alkene. The reaction follows SN1 pathway when the alcohol is secondary or tertiary, about which you will learn in higher classes. However, the dehydration of secondary and tertiary alcohol to give corresponding ether is unsuccessful as elimination competes over substitution and as a consequence alkenes are easily formed. Can you explain why? Why is biomolecular hydration not appropriate for the preparation of ethyl methyl ether? Second, Williamson synthesis. It is an important laboratory method for the preparation of a symmetrical and unsymmetrical ether. In this method, an alkyl halide is allowed to react with a sodium alkoxide. Ether containing substituted alkyl group, secondary or tertiary, may also be prepared by this method. The reaction involves SN2 attack on an alkoxide ion on primary alkyl halide. Better results are obtained if alkyl halide is primarily in case of secondary and tertiary alkyl halide. Elimination competes over substitution. If a tertiary alkyl halide is used, an alkene is the only reaction product and no ether is formed. For example, the reaction of CH3ONA with the CH3CBr gives exclusively to methyl propene. It is because alkoxide are not only nucleophile but strong bases as well. They react with the alkyl halide leading to the elimination reaction. Phenol are converted to ether by this method. In this, phenol is used as a phenoxide moiety. Physical properties. The carbon-oxygen bond in ether are polar and thus ether have a net dipole moment. The weak polarity of ether do not appreciably affect their boiling point, which are comparable of those of the alkenes of comparable molecular masses but are much lower than the boiling point of alcohol as shown in the following cases. Formula: N-pentane, ethoxymethane, butanol. Boiling point 301, 307, 390. The large difference in boiling point of alcohol and ether is due to the presence of hydrogen bonding in alcohol. The miscibility of ether with water resembles those of alcohol of the same molecular masses. Both ethoxyethane and butane 1-ol are the miscible to almost the same extent, that is 7.5 and 9 gram per 100 ml water, respectively, while pentane is essentially immiscible with water. Can you explain this observation? This is due to the fact that just like alcohol, oxygen of ether can also form hydrogen bonds with the water molecule as shown. Chemical reaction. Ether are the least reactor cleavage of carbon oxygen bond in ether. Ether are the least reactive of the functional group. Cleavage of the carbon oxygen bond in ether takes place under drastic condition. With excess of hydrogen halide, the reaction of dialkyl ether gives 2-alkyl halide. Alkyl aryl ether are cleavage at alkyl oxygen bond due to the more stable aryl oxygen bond. The reaction yield phenol and alkyl halide. Ether with two different alkyl groups are also cleaved in the same manner. The order of reactivity of hydrogen halide is as follows: Hi, HBr, HCl. The cleavage of ether takes place with the concentrated Hi or HBr at a high temperature. However, when one of the alkyl group is tertiary group, the halide formed is a tertiary halide. It is because in step 2 of the reaction, the departure of a leaving group creates a more stable carbocation and the reaction follows SN1 mechanism. In case of anisole, methyl phenyl oxenium ion is formed by protonation of ether. The bond between OCH3 is weaker than the bond between OC6H5 because the carbon of the phenyl group is sp2 hybridized and there is a partial double bond character. Therefore, the attack by I negative ion breaks OCH3 bond to form CH3I. Phenol do not react further to give halide because the sp2 hybridized carbon of the phenol cannot undergo nucleophilic substitution reaction needed for conversion of the halide. Electrophilic substitution. The alkoxy group OR is ortho-para-directing that activate the aromatic ring toward electrophilic substitution in the same way as a phenol. Halogenation. Phenylalkyl enter ether undergo usual halogenation in a benzene ring. Example: anisole undergo bromination with the bromine in ethanoic acid. Even in the absence of iron molecule, bromide catalyst. It is due to the activation of a benzene ring by methoxy group. Para isomer is obtained in a 90% yield. Friedel-Crafts reaction. Anisole undergo Friedel-Crafts reaction. The alkyl and the acyl group are introduced at the ortho and para position by reaction with the alkyl halide and acyl halide in the presence of anhydrous aluminum chloride or Lewis acid as a catalyst. Anisole plus CH3Cl gives out 2-methoxytoluene and 4-methoxytoluene as a major and minor product. Nitration. Anisole react with a mixture of concentrated sulfuric and nitric acid to yield a mixture of ortho and para nitroanisole, which is a major and a minor product. Here are some in-text questions of these chapters. I hope you enjoyed the lecture. Thank you so much.